Okay, next topic is fundamentals of combustion kinetics, chemical kinetics. So, this is very important to understand how fast the reaction is going to be completed. Okay. Okay, so chemical kinetics or combustion kinetics is used to evaluate the rate at which a reaction takes place. It is very important for us. So, see for example, if there is a combustion chamber, okay, so there is inlet and there is a outlet. So, these products leave here, products and the reactants enter. Okay. So, some dimension we will keep for this, say L. So, reactant, let us premix the fuel and oxidizer. That reactant enters at some temperature, say T reactant temperature, and the product leave at T product. So, some heat transfer is allowed to take place from this control volume. So, now if L is the length of the combustion chamber, these reactants are entering at some velocity. So, say VR is the velocity of the reactants. So, I want to burn more amount of reactants, okay, more amount of fuel. So, more amount of, for that you need to supply enough amount of oxidizer. So, the reactant is supplied at a particular flow rate or a velocity, say VR, okay, and reaction is expected to be completed within this length. So, if you do not have an idea of whether the reaction will be completed within this length, that means the time available for the reaction to complete is this length divided by VR. So, that is the velocity. So, this is length is in meter per second. So, this is the time scale, time available, I will say. So, time available for the reaction to complete is the length divided by VR, velocity at which the reactants are passed. So, this is the time available, whether the reaction will be completed within this time. If not, I have to either increase the length or reduce the velocity. If I do not do this, the time available will not be sufficient for the reaction to complete. So, the product will not be formed completely. So, the reactant may come out. So, the rate at which the reaction takes place is very important to determine. At least we should know some idea, okay, of about that, or else we cannot construct the combustion chamber. The proper dimensioning cannot be done. So, this study of chemical kinetics is very important in determining the rate at which a chemical reaction will be complete. And we have to understand several things here. How a particular fuel is going to react, at what are the factors influencing the chemical kinetics and so on. Okay, so, the rate of reaction basically depends on two things, temperature and the concentration of the reactants. So, if you have good volume of reactants and good temperature, okay, so if both are available, then the rate of reaction will be sufficiently fast. So, we will see one by one. So, first of all, let us take some reactants, okay, it's like say methane and air combustion. So, when a reaction represents the overall reactants, like methane the fuel, air is the oxidizer, and products are the major products. Okay. If I write a reaction like this is called global reaction. Global reaction in the sense, I know what are the reactants, okay, and I write this in the mole base, like 1 kilomole of methane reacts with so much kilomoles of air, forming 1 kilomole of carbon dioxide, 2 kilomoles of water vapor and so on. So, this global reaction actually is will give you an idea of the overall mechanism representing the global reactants and the major products. However, this global reaction cannot occur in a single step. So, I have written in a single step like this. Okay. So, reactants give forming products. In a single step I am writing this, but it is impossible for the reaction to occur like this. Okay. Or one more thing is, we can see this arrow, this is one directional arrow, that means the reactants can form products, but products cannot form. We have already discussed this. The product cannot form reactants like the CO2 and H2O. If you put in a combustion chamber, it will not produce the required reactants. Okay. So that means that is impossible. So you can even think about this. It is not impossible, because this has several steps into account. It is not going to complete in only 1 second. That is, it has some definite time for completion and it has several steps. So methane CH4 is not going to directly convert into CO2 and H2O. So the number in front of the species represent the number of moles. So here 1 kilomole of CO2, 2 kilomole of H2O, etc. So that means we are not talking about the molecular level. We are talking about the see, what is 1 mole? Several number of molecules contributing a mole. So we are talking about several molecules present in this particular scheme, reaction scheme. But if you can write the reaction in molecular level, then only we can say that is that can happen in one step or not. Okay. So global reaction cannot happen in one step, single step. That is for sure, and we have to understand. So it is not reversible. Okay. So how it occurs? It occurs in several steps. The global reaction usually occurs in several steps. Okay. These steps are part of a chain reaction, which can be divided into 4 stages. Chain reaction. So what happens is, the reactants should break. For example, O2 should break to O atoms, CH4 should break into say CH3H and so on, CH2, H2. So several ways the reactants are going to be disintegrated, and because the bond should be broken. So in one step only one bond can be broken and one bond can be formed and so on. So in that case, if the reactants collide with each other, they can lose one of the bonds and form one of the bonds and so on. So this initiation step is the first step, during which the reactants are disintegrated, and what is formed are called radicals. Radicals or some species which are formed due to that first step, initiation step, which is much reactive, highly reactive than the reactants themselves. Okay. Now the second stage is called chain propagation. The chain has been initiated first, and this chain reaction is now propagating to the next step, producing 2 types of species. One is called metastable species. Name itself suggests metastable. It is not completely stable. Stable species, say CO2, H2O, they are stable species, much stable. But metastable they are not so weak, but they are not strong also. They are metastable. So they can under certain conditions they can react with some other species to form products, or some other species again. So then again the highly reactive species called radicals are also formed in the chain propagation reaction. So chain propagation keeps the reaction, the mechanism alive. Next, the third stage is called chain branching. Actually this is a very important stage where multiple radicals are formed. So for example, in chain propagation only one radical may be formed. Let us define radical later, see that in detail. But in the chain branching step, multiple radicals are formed. More than one radical can be formed. Okay. Once the radical concentration increases, the reaction rate is accelerated. The overall reaction rate is accelerated. So it may also end up in explosive nature of that. Explosive, much faster reaction can happen. So this is called chain branching step or stage. The final stage is called chain termination step, where the major products, stable products like CO2 and H2O are formed due to the reaction between radicals. Okay. So actually, even though we can categorize this in 4 stages, all occur simultaneously. All these 4 stages occur simultaneously. Okay. the reactions which are contributing to the chain reactions mentioned above, the 4 steps, stages of chain reactions, they are called elementary reaction, as opposed to the global reaction. They are called elementary reactions. They are molecular level reactions, can occur in one step, plus they are reversible also. Okay. So, this is the global reactions cannot occur in one step, they are not reversible. Elementary reactions are molecular level reactions, global reactions are molar level reactions, and elementary reactions are reversible and they can occur in one step, single step. Okay. So, now I have given some elementary reactions here and also indicated the chain stages, chain reaction stages. See, for example, as I told you, oxygen breaks. Now, please understand that here there is a contribution from a third body called M. Normally, M represents third body, it may be other species, a group of other species. See, the oxygen can collide with any other species, like even some partially formed products. So, CO, CO2, anything can be used to collide with oxygen. So, this M can be anything, and but that particular species is heavier, and they may be the walls also, even the wall of the reactor. So, that will contribute to just breakage of the bonds. So, for example, O2 breaks to 2O. Okay, now you can see that O2 with CH4, they are reactants basically, can form HO2 and CH3. So, one of the methane H is now disintegrated and CH3 is formed, and that H reacts with O2 to form HO2. This HO2 is the metastable species I am talking about. This is a metastable species. Correct. So, this O is a radical. So, actually O, OH, H are radicals. They are very reactive, very reactive thing, species. This HO2 is a metastable species which is formed here. Okay, again CH3 should again undergo some more disintegration. So, CH3, one more H will break to form CH2 and CH will form and so on. So, this is one step where the methane is broken into CH3 plus that H is contributed to formation of HO2. Similarly, CH3 now breaks and so on. So, several reaction steps are there in this. I have just listed this few. Similarly, this also can happen. So, CH4 with the third body can produce CH3 plus H and so on. So, when the reactants are disintegrated, initiation steps are got. Now, chain branching. Chain branching is, I told you, multiple radicals are formed. So, H plus O2 giving O plus OH. So, both are very reactive. So, similarly, OH splitting into O and H. So, you can see multiple radicals are formed, or this is very fast reactions, chain branching. This will lead to acceleration of the overall reaction rate, chain branching steps. Okay. Then I have several propagation steps. In propagation step, you can see that one radical is surely formed. Here this, similarly in this reverse reaction here you can see this. Okay. So, similarly you can see O2, CO is also very highly reactive, and you can see H, etc. Okay. So, in the reverse reaction OH is formed. So, when radicals are involved, and these reactions will maintain the chain, so that to propagate. Okay, it may not accelerate the chain reaction as the branching reactions do, but they will maintain the chain reaction and till its completion, total overall mechanism complete. But termination reaction, if you see that the radicals recombine, this is called recombination, H plus OH giving H2O, CO plus O giving CO2, they recombine to form the final products here. So, here you can see that CO plus OH giving CO2 plus H, here also a final product is formed. Similarly, OH plus H2 giving H plus H2O, a final product can be formed. When the final product is formed along with the radical, that is called propagation reaction, but only if the final product is formed like this, then that is a termination reaction. So, these are the steps in the chain reaction: initiation, branching, propagation, and the termination reactions. And you can see that for methane, we can define say about 400-500 reactions like this, and everything should be properly understood. So, these all are reversible reactions. See the arrow here, these are reversible reactions and the molecular level reactions. So when I say O2 giving 2O, I indicate that one molecule of O2 reacts to form 2 atoms of O and so on. So everything is molecular level reaction. Okay, now radicals. Species such as HO and OH are called radicals, and species like HO2 are called metastable species. Okay, radicals are initially formed through chain initiation reactions. So we have already seen that. Okay, now radicals have unpaired valence electrons, which make them very reactive. Okay, unpaired valence electrons make them very reactive. So these electrons are fond of reacting with the other radicals or other species. So basically they have very short life. They partner with other radicals or other species to form covalent bond, that is molecular level bond are formed. When they react with the other species or molecular covalent bonds are formed. So chain propagation reactions produce radicals along with metastable species or stable species, final products also. Okay, that is very important. So these keep the reactions running till it completes totally. Chain branching reaction lead to rapid production of radicals, more than one radical at a time, so that the reaction may become explosively fast, very much rapid. Okay. The reaction comes to completion through chain termination reactions where the radicals recombine. So two radicals, when they are formed as separate radicals, they can recombine to form the final products, which we have discussed. Okay. So the global reaction which is given here like this will not occur in one step. You can also assume, see, several molecules are there here. Only two molecules, if they want to hit each other and form products, disintegrate themselves and form products, that is possible. But so many molecules, it is not possible to really sense. So this is only mechanism, overall mechanism represented by a global reaction, which gives what are all the reactants present and what are the final products which are formed. Okay, that is the important thing here. So these reactions, elementary reactions, are molecular reactions and are reversible reactions. Several of these steps will contribute to a global reaction. So several of these steps written in a particular order is called mechanism, reaction mechanism, and that reaction mechanism will contribute to, say, methane air reaction or hydrogen air reaction and so on. Even a simple hydrogen oxygen reaction has about, say, 15-20 steps, reaction steps like this. Okay, now in the 4 chain reaction steps, initiation, propagation, branching and the termination, radicals, metastable species are formed. Then you can see that the chain branching reactions will be very fast, and chain propagation reactions maintain the reaction by producing a particular radical or metastable species along with a stable species. Then the termination reactions consumes the radicals to form the final products. Okay. Now chemical kinetic mechanism, as I told you, a global reaction which is expressed in terms of moles of reactants and moles of products. Okay, is not going to occur in one step, and it needs several elementary reactions to define its pathway. So for example, if I say methane oxidation, the methane oxidation has a definite pathway or several types of pathways, and for that we need to know the entire mechanism by a set of elementary reactions which will define the pathway. Okay, but so then why is global reaction is useful? Because it gives the overall idea of the reactant species and the major products which are formed. So that is what is very important for heat calculations. When you want to calculate heat, etc., that is what is going to be. So what is the heat release rate? So when you want to know what is heat release rate, a single step global reaction is enough for us. Similarly, when you want to calculate the amount of air required for a amount of fuel fed into the reactor, single step reaction is enough. Okay. Now how can you say that for heat calculation only one step is enough when, say, 400 or 500 steps are going to be involved in giving the mechanism of the entire reaction? Because of this, heat of a reaction calculated using a single step global reaction is equal to the summed up or the net heat of reactions of all the elementary reactions constituting the mechanism through which the global reaction takes place. Okay. So, you calculate the heat of reaction using a single step global reaction, you will get a value, say that is x1. You have the mechanism now. So, 300 steps, elementary reactions, 300 elementary reactions contributing to the major the entire mechanism, and calculate the heat release from this, add and subtract them, and evaluate the total the net heat of heat release, etc. So, that may be x2. Hess's law of summation says that x1 will be equal to x2. You calculate the heat based upon a single global step reaction or several elementary reactions, okay, the result is same. So, heat calculation is concerned, you can just complete it by using a global single step reaction itself. Okay. So, for a practical reactor design, when you want to know how much oxygen should be, air should be supplied, okay, then what should be the product coming out. So, what should be diluent, say amount of diluent like nitrogen, how much should be supplied, okay, what is the heat which is released during this process, etc. The mechanism, the global single step is enough for us. We do not need to go for the detailed mechanism with elementary reactions. However, for accurate temperature calculation, so even this global single step reaction can give some idea, some order of temperature. See, if the temperature, actual temperature say is 2200, it may give a slightly higher temperature, so 2300 or 2400, something like that. But if you want accurate temperature calculations, okay, then you should go for mechanisms or time for ignition. So, these are very important things. So, time delay, for example, how fast the ignition will occur, or what is the time delay between the ignition source provided and the actual ignition to occur, or now under what conditions the flame will blow off. So, this type of instabilities or transient time dependent processes, when you want to take into account, a thorough knowledge of the reaction mechanism with important elementary reactions is necessary. Reaction mechanism can be as complicated as possible, but at least we should know the sensitivity of these elementary reactions and choose proper important elementary reactions to constitute a reaction mechanism that will give you idea of these factors. Okay. So, that is what is important. So, we need to know about this. So, we know that when you handle with several elementary reactions, you are going to, your analysis is going to be complicated, because you are going to solve several reactions together. Instead of just taking one reaction at a time and solving it, it is easier to do this. But if you want in several cases like this here, you need to go for some elementary reactions which will give you accurate calculations. Okay, now molecularity of an elementary reaction. An elementary reaction is written at the molecular level, we are told that already. So, let us consider an important reaction called CO plus OH reversibly giving CO2 and H. So, this actually can be read as one molecule of CO reacts with one molecule of OH to produce one molecule of CO2 and one H atom. So, now if you take the forward reaction, two molecules are involved. So, the molecularity of this reaction is 2. So, number of molecules participating in a reaction, that is the molecularity. Obviously, a global reaction does not have a definition of molecularity, because that is written in terms of moles. So, I cannot say 1 mole of CH4 plus 2 into 4.76 moles of, so that they cannot translate into molecules. So, that is not possible. Global reaction is not a molecular level reaction. But elementary reactions, molecularity is the number of molecules which is participating in a particular reaction. See, for example, if you take this reaction CO2 reversibly giving CO plus half O2, the forward reaction, the molecularity is 1, because one molecule of CO2 is involved, okay, and so on. So, so here also you can see that the reverse reaction, you can say the molecularity is 2. So, this is O, half O2 can be written as O. So, CO plus O giving CO2 and so on. Okay. So, this reaction, elementary reaction, take place in one step. So, when it reacts, one bond is broken and one bond is formed. So, that is what can happen in one collision. What I say, the collision should be proper. So, that is what I have written here. CO molecules collide with an OH molecule with necessary force. It cannot just collide like without any energy, okay, with necessary energy and force and proper orientation to break the bonds in them and form new bonds. So, at a time one bond can be broken and one bond can be formed. So, that is possible in elementary reaction at molecular level, what we are talking here. Okay. So, again you can see that similarly at the prevailing temperature, based upon the temperature, reverse reaction also can happen and the CO and OH can be formed. So, this is also very important. So, under some conditions the forward reaction will be favorable, under some conditions reverse will be favorable. This we have already seen in the chemical equilibrium. So, the amounts of CO, OH, CO2 and H present are dependent on the equilibrium constant which we have calculated. That is again a function of temperature and pressure. Okay. So, this elementary reaction can occur in single step. It is a reversible reaction, and based upon the number of molecules participating in the reaction, its molecularity is defined. Okay. Then what is the order? Order of a reaction. So, that is what we are going to see, this order of a reaction. Molecularity of most of the reactions is 2, because 2 molecules can collide and reaction can be favorable. Probability of more than 2 molecules colliding with each other during a reaction is much lower. So, only a few reactions, very few reactions of molecularity, 3 molecules at a time colliding and forming, only very few reactions are there, very few, we can just number them. Okay. So, but more than 90-95% of the reactions are 2 molecules colliding with each other. That is, the molecularity of those elementary reactions are 2. Okay. Now, dissociation reactions, I told you the molecularity is 1, CO2 giving CO plus O. So, that is molecularity is 1 there. Okay. Now, for defining the order of the reaction, we need to know how the rate of a reaction is defined. So, how the rate of reaction is defined? It is defined using what is called law of mass action. Okay. What is law of mass action? The rate of a chemical reaction is proportional to the concentrations of the reacting species. Okay. Raised to some powers, appropriate powers. So, that is the law of mass action. So, for example, if A plus B gives C plus D, okay, I am considering the forward reaction in this elementary reaction, then the rate of the reaction, okay, so I will say rate of the reaction is nothing but what? Rate at which the concentration of a reactant reduces with time. Reactant concentration reduce, the product should be formed, so the concentration of product increases. So, this is proportional to the concentration of the reactants raised over some power. So, M and N are some appropriate powers. Okay. So, this is called law of mass action. The rate of a reaction. So, when I put say like this means concentration of A. Concentration is nothing but this is kilomole per meter cube, that is the concentration of A. So, concentration of A, how it varies with time, the rate of change of concentration of A with time is proportional to the concentration of the reactant species. A and B are the reactant species. So, A raised to some power M, B raised to some power N. So, how, okay, now these powers can be integers or decimal numbers, we have to see, okay, based upon what type of reaction it is. So, now what is order? Once you know the law of mass action, I know the reaction rate depends upon the concentration raised to appropriate powers of the reactants. So, order of the reaction is the sum of powers of the concentration of the reacting species in the rate equation. This is called rate equation. The rate at which A reduces with time. We can also write rate at which B, concentration of B reduces with time. That is also proportional to A power M and B power N. Correct. So, here the order is nothing but M plus N. The powers of A, concentration of A is M, the power of concentration of B is N. So, the order of this reaction is m plus n. Okay, so, this is what the definition of order is. So, law of mass action defines the rate of reaction as that is proportional to the concentrations of the reacting species raised to appropriate powers, and the order is defined as the sum of the powers to which the concentrations are raised to. Okay. Now, order and molecularity of an elementary reaction is same, both are same. So, they will have the same value. See, for example, CO plus OH giving CO2 plus H, the molecularity is 2. We can see that CO, OH 2 molecules are positive. What is saying this? When you write the rate of this reaction, okay, let us say forward reaction here, the rate at which the concentration of CO changes with time, dCO by dt, square bracket when I put, that is the concentration of CO, correct. So, this is the concentration of CO. The rate at which the concentration of CO varies with time is proportional to concentration of CO raised to power 1 and concentration of OH raised to power 1. Okay. So, now this is the law of mass action. The proportionality constant is not a constant, but it is defined as rate coefficient, which is K. So, K is the rate coefficient. Now, you can see that the order of this reaction is 1 plus 1 2, molecularity is also 2, order is also 2. For elementary reactions, the stoichiometric coefficient here for CO is 1, stoichiometric coefficient for the OH is 1, that is 1 molecule of CO, 1 molecule of OH. So, that is only used as the power to raise the concentration. So, CO power its molecule number of molecules, similarly OH power number of molecules. So, when you add them, that will be the molecularity. So, order of the reaction and molecularity will be the same for an elementary reaction. Okay. Order of a reaction is defined from elementary reaction. It is defined for global reaction also, but molecularity is defined only for the elementary reaction. Okay. Now, the rate at which reaction takes place is the rate at which the concentration of CO varies. Now, in this case it is a reactant, so it should decrease with time. So, that is what we are representing like this. The rate of reaction is, we can write CO by dt, it is actually negative, will be equal to dOH concentration by dt. Both are same, correct, because the rate at which this is decreasing, CO is decreasing, one molecule of CO if it partially consumed, then the same amount of OH should be consumed to form the products. So, we can write like this. Okay, so, it is easy to note that the same rate OH will decrease with time, and in the same rate the concentrations of CO2 and the concentration of H will increase with time, correct. So, these are actually negative, and this should be equal to dCO2 by dt, which is equal to dH by dt. The rate at which the reactants are consumed, that will be the rate at which the products are formed. Okay. So, this is the important thing we should remember, and the order of the reaction is the powers at which this concentrations are raised to in a rate equation given by the law of mass action. So, that will be, for this reaction will be 1 plus 1, which will be equal to 2, same as the molecularity. Molecularity for elementary reaction, order of an elementary reaction is the same.